Ladies and gentlemen, you're most welcome to this evening. And as shown on the slides, this is a special session on energy. But let me first explain you the conceptual framework behind this session. As you know, the F in FOM is for fundamental research. And the key question, of course, is fundamental research in which areas? Well, and it is very clear that we will have to balance certain things. Of course, there is the interesting and intrinsic development in physics itself. What you most of the time are doing as you are pushing forward the frontiers of science and you follow your own curiosity. That's what some of us may call following the international agenda or physics for physics. But however, in the present situation it is also very clear that nowadays you have also to explain what physics can contribute to the problems in society. And physics in society is an issue we have to take serious because as I earn part of my salary by advocating in the centers of government money for science, money for physics, then it is clear that in the future we will have to explain what we can contribute to society, and if, for instance, 50% is on the basis of this type of argument, then society and politicians, as they are not always narrow-minded, will just grant us our own kind of hobbies. Now, as far as physics for society on the next slide is concerned, you can make a distinction between, for instance, cooperation with industries. We in FOM, we have the industrial partnerships with industries. And this is important in the Netherlands because we are, I think, in a very special situation since in our country a number of multinational or international companies have their research bases. We're talking here in the Eindhoven area about Philips, about ASML, but of course there is also Shell, there is OC, there is Unilever, and that in itself, the very fact that the knowledge production is for an important part within the Netherlands is, I think, something which is beneficial for our society. Another issue which is clear is the energy problem, and that's going to be the main theme of tonight. And we in FOM are also struggling with the question how we can contribute to the important issues within the health situation. Now, the next slide just shows the companies we are at this moment working with. We welcome their representatives and also the representatives of the companies of which the logos are not ready there. But you never know. Now to the main theme of this evening, energy. As the next slide shows, we have three kinds of contributions. The first is the governmental view. And I will explain later by introducing Chris Buijink for the Ministry of Economic Affairs. And then a very important contribution coming, the physics approach, Nobelprijswinnaar Steve Chu. And then at the last, there is, but certainly not least, a key FOM person from our organization, Niek Lopes Cardozo. Let me now go to Chris Buijink. Chris Buijink is Secretary General of the Ministry of Economic Affairs, or Trade and Industry, or whatever the country is you are coming from. And to my personal opinion, the Secretary General, by the way, is the highest civil servant in the ministry. And it's my personal opinion that Chris is the best informed Secretary General in The Hague about research and innovation. This has everything to do with the fact that before he became the Secretary General, he was the Director of Innovation in that ministry. And unfortunately, but it is also a personal remark, there are not many Secretary Generals in The Hague very familiar with our area. But anyhow, Chris is. Chris is new in his job. And in January, there is always an interesting thing in the Netherlands, because in January, the Secretary General of the Ministry of Economic Affairs writes an article in some kind of magazine, which is called Economisch-Statistische Berichten. Forget the Dutch. And here he has to be something of a balance act. Because if he just writes what his minister thinks, they say, okay, his master's voice. However, if he goes a little bit away from the minister and a little bit too far away, there is a problem. And as I remember well, but he doesn't have to confirm it, one Secretary General was sacked one time because the minister did not approve it. So there is an interesting balance act on January always. And this time, Chris hit the newspaper with this article about elderly people, they're on the bicycles, and younger people getting to work. Chris is now going to tell us something about energy. And we are, at least a large part of this audience, very curious to know what he is going to say, because the physics community, the chemistry community, and some part of the biology community, they all made plans for energy research, and they are somewhere now in The Hague, and we hope that Chris is in a position to tell us something about what the covenant views are with respect to energy and energy research, so that somehow the scientific community can interact. Anyhow, there is a whole auditorium with people who are now just wondering what you are going to tell us, and may I invite you to the stage.
Well, ladies and gentlemen, dear Hans, what a crowd. I thought it was a shortage of betas in this country. It is a real pleasure to represent Maria van der Hoeven, the Economics Affairs Minister, and to address such a large and distinguished audience, the FOM community, from science and enterprise on energy and energy research. I feel a bit like the block of commercials ahead of the main movie, Dr. Chu, but I'll do my best not to keep you waiting too long for the main movie. I will discuss the past and present energy situation, the technological options available to solve the energy problem, and actions both on the European and the national level in preparation of a transition to a more sustainable energy system, as well as the role, yes, Hans, of energy research and development. I'm not sure I'm going to answer all your questions, but I'll do my best. There is a difference, maybe, in approach between scientists like most of you and people in the policy-making parts of The Hague. You are, I think, primarily interested in theoretical and applied research and the resulting technologies. Our interest is first and foremost in the importance of energy to the economy, concrete solutions on the marketplace. Both improved technologies and economic potential are a sine qua non for successful innovation. And probably all of us agree that energy technology is as old as the human race. As Professor Chu, together with Professor Goldenberg, put it so eloquently in the preface to the Inter-Academies Council study, Lighting the Way, human prosperity has been intimately linked to our ability to capture, to collect, and to harness energy. And of course, it all started with the control of fire. And here in these parts of Europe, wind power was already used in our golden age to reclaim the lakes north of Amsterdam like the Beemster, a technology forever associated with the name of Jan Adriaans van Leegwater. And science is a series of names, of icons who led the world in discoveries. Less than 300 years ago, Thomas Newcomen constructed the first steam engine with an efficiency of less than 1%. James Watt took it to 19%. And then in the 19th century, from Sadi Carnot to Thomas Edison to Nikola Tesla, in the 20th century, Fermi, Hyman Rickover, and just after the World War, the tokamak designed by Igor Tamm and Andrei Zakharov. The point of this series of names is to highlight that over the last 50 years, hardly any new developments occurred in the field of energy production. What we saw was the improvement of existing technology. History of energy production teaches us a couple of general lessons. One of them is related to the price of energy and income. 4 centuries ago, the price of wind power was very high compared to the pay of a common man. Over time, a shift occurred in the opposite direction. This has been accompanied by an enormous increase of productivity and per capita consumption. The population in the industrialized world represents about 20% of the global population. It consumes about half of all available energy every year. And if the remaining 80% would have the same standard of living, global energy consumption would at least double. And moreover, the world population itself will grow from about 6 billion people in 2000 to 12 billion in 2050, another doubling. And the increase of energy consumption logically follows this trend. The IEA, International Energy Agency, expects an increase in energy consumption between 2005 and 2030 of 55%, 45% in China and India. We may expect at least a doubling of global energy consumption by the year 2050. And the agency appeals for vigorous, immediate and collective policy action by all governments to move the world in a more sustainable energy direction. The challenge for all of us is to put in motion a transition to a more secure, lower carbon energy system without undermining economic and social development. I believe this must involve the development and application of an improved energy technology, including nuclear fission. Today's high oil prices will help the development of new and better technology. For energy is not only a concept of physics, economy, as I said, also play a role. Physicists predict a theoretical efficiency of about 85%. In reality, the most efficient machines, such as combined cycle gas turbines and ship diesel engines, do about 60%. That figure of 60% depends on the price of fuel, economics. With higher fuel prices, we can apply better and more expensive technology and increase efficiencies. From an economic point of view, 70% should be feasible in the near future. And meanwhile, everybody is about aware of what CO2 emissions are doing to our planet, how to avoid these negative consequences and how to bring down emissions. 1 year ago, more or less, the Stern report was published on the economics of climate change. Lord Stern found that global CO2 emissions should be reduced by at least 60%, perhaps 75% in 2050. A large-scale uptake of a range of clean power, heat and transport is required for radical emission cuts in the medium to long term. And although many of the technologies to achieve this goal already exist, the priority is to bring down their costs so that they are competitive with fossil fuel alternatives under a carbon pricing policy regime. And the report also states that public spending on energy research, development and demonstration projects has fallen significantly in the last 2 decades and is now low compared to the money spent on other sectors and industries. The challenge to the industrial world is clear. We should increase global energy production fourfold while cutting CO2 emissions by 75%. In other words, the CO2 emission per joule we should reduce by at least a factor of 10, preferably before the year 2050. And the number of technological options is limited. First, energy conservation, including possible gains in efficiencies. Second, there are a few supply-side options: solar power, wind power, and geothermal energy. Nuclear power, both sustainable fission and fusion, and to a lesser extent, biomass. Finally, there are the technologies to adapt supply and demand, and the technologies to mitigate environmental consequences, such as energy storage, including electricity and hydrogen, smart electricity grids for the bulk transport of energy, and carbon capture and sequestration. The FOM roadmap mentions most of these options, as do the energy proposals FOM presented to the Dutch government last summer. Allow me to make 3 observations. The first is that affordable energy storage could help to shave peaks in the irregular production and consumption patterns, especially as it would help to adapt to renewable electricity sources having a fluctuating character. My second observation is that we can probably not afford to ignore any of the options I mentioned. I refer especially to nuclear fission. We still possess excellent facilities for research and education in these areas, and we should use them. My third remark concerns nuclear fusion. As you all know, and you better than I, it turned out to be extremely difficult to harness the power of the sun on Earth. Nevertheless, there is reason to be really impressed by the scientific and technological achievements in this field, such as the development of equipment to heat the fusion plasma locally and to stabilize the fusion process at the same time. These achievements, also of FOM scholars, would, in my opinion, be worth an Olympic gold medal in science. But it's not for me to decide. Of course, as Professor Chu also writes in the report Lighting the Way, the commercial use of this technology is still far away. Some ITER partners anticipate demonstration fusion power plants about 2035 and commercialization about 2050. Allow me to turn to the messages of Lord Stern and Al Gore. In a star-dusted way, they have set things in motion also for the public at large, both at the European and on the national level. The European Union's 7th Framework Technology Programme started last year. Energy, I'm sorry to say, is not a very prominent part of this programme. But because of the emerging energy problem and the growing consciousness awareness of the challenges we face, the European Commission decided to develop a strategic energy technology plan. It proposes to launch 6 initiatives in the areas that I mentioned. And the Commission reminds us that today's expenditures on energy research by European governments on the development of the energy technologies amounts to only a quarter of their value in the 1980s. Based on the expenditures a quarter century ago, current outlays should now be around 2.5 billion euros per year, and they are not. The European Commission aims to increase both national and European funding on energy research. At the European level, the budget should be doubled for the 8th Framework Programme, and the current annual budget in the 7th Framework Programme for energy issues is 880 million euro. It is expected that the European annual budget will rise to 1.75 billion euro in 2014. I'm confident on the future budget increases at the European level, but also at the national levels, member states level. In the coming years, we should have more money spent on energy innovations. In the Netherlands, I would like to mention 3 national initiatives. The first is the energy transition approach. The previous government developed a transition action plan whose goal is a 50% cut in domestic CO2 emissions in the year 2050 compared to 1990. The plan calls for a sustainable energy supply on 7 areas, including green feedstock, sustainable mobility, renewable electricity, industrial efficiency, sustainable construction, and sustainable glass houses. Each area has its own public-private platform with representatives from industry, scientific and public organizations, as well as national, regional, and local authorities. Some of the presidents of the platforms are present here tonight. The Dutch government has pledged to increase its annual budget for energy innovation from about 2.3 billion euros for this year to 2 billion euros in the foreseeable future. The second initiative is schoon en zuinig, or as we say in English, clean and green. The goal of this project is threefold. 2% energy savings per year within a few years, or a doubling of the reduction rate now. 20% sustainable energy in 2020, and 30% reduction in greenhouse gas emissions in 2030, a more ambitious target than is posed at European Union level. The ambition of this project, Greening the Netherlands, is to transform our country into one of the cleanest energy areas in Europe, coupled to one of the lowest per capita energy consumption levels. 3 consecutive waves of measures are being pursued in close collaboration with the most important stakeholders. The first wave involves short-term progress by taking measures which are already available. The second wave aims to prepare for progress. It includes an acceleration of demonstration projects and innovation in the medium term. And the third wave is directed towards further long-term innovations, especially by intensifying all the efforts in the area of energy transition, which should develop into a permanent source of innovation. The government plans to increase its annual budget by 140 million euro for this year, rising to 500 million euros annually for the years to come, an increase of more or less 30%. Come this spring, the government will publish its new energy report, its energy vision. A vision that will be based on 3 pillars. Energy has to be clean, affordable, and secure. And the report will address 3 important issues: the future access to energy resources, our future energy infrastructure, and the mitigation of possible consequences for the public and Dutch industry of significant changes in our energy supply. In order to be able to adapt to the new international environment, a strategic vision on the future energy situation, including a possible change in our national energy policy, is warranted as well. In addition to these initiatives, I would like to mention the R&D efforts of our national energy research institutes in Petten, ECN for non-nuclear research, and NRG for nuclear research, and they together receive about 50 million euro a year in annual grants. It is essential that the people of Petten cooperate both with industry and science institutes throughout the nation. And this is the case, happily. 2 projects I would like to mention in particular. The first is in the area of future power electronics and smart grids. It involves close cooperation between KEMA, the technical universities of Delft and Eindhoven, and ECN. And the outcome is that a world-class laboratory in the field of power electronics will be opened at KEMA in Arnhem in April this year. The second cooperation project is still in the preparatory phase. It involves research into the technologies of advanced energy, including materials. ECN, NWO, FOM, and the technical universities, some other groups, are involved. And precisely at this time, a special committee led by Hans de Wit is looking into these proposals to prepare an advice to the government to be decided on in the month to come, Hans. Finally, I would like to, and you mentioned it, Hans, to salute the work that's been done by FOM, for instance, through the Industrial Partnership Program in making the bridge work between research and business. And already a lot of companies are participating in this partnership. More could follow. I think it's extremely important for all the things we will have to do in the coming years. Even more important in this respect, also looking across this hall, is the function of FOM, as so to speak, as a breeding ground or house of researchers, workers for industry, for entrepreneurship, and for society. In concluding, I would like to recall the innovation lecture. Some of you were there, I know, held this year by Jeremy Rifkin last year on the 4th of December in the Hall of Knights in The Hague. His lecture was called Leading the Way to the Third Industrial Revolution, with the subtitle A New Energy Agenda for the European Union and 21st Century. And his message was that this third industrial revolution will be based on 3 pillars: renewable energy, energy storage technology, and thirdly, smart, sometimes small, power grids. There is much work to do in these areas to make that third revolution happen. But together we could do it. Jeremy Rifkin's dream as an American is that Europe could show the way in this respect. It is my dream that the Netherlands will be the front runner of Europe, as we already excel, for instance, in smart grids technology. I've offered you, ladies and gentlemen, a small bird's eye view of our energy research programs, our plans to make our energy supply more sustainable in the future. This should be our common endeavor. We together, policymakers, scientists, people from industry, together we have to find the right solutions that will allow us all to rise to the challenges of fulfilling the ever-increasing need for energy in a sustainable way, to the challenge to green our world while ensuring at the same time the further rise to prosperity of all its citizens. Thank you.
Maar die foto pas erop als ik het jaar 1997 noem. Dus even nog niet.
Eerst even Chris Buijink.
Huh? Dus ik ga 1997. Ja. Als ik dat zeg, dan komt hij. Wacht maar even. Ladies and gentlemen, it is on the Tuesday in the second week of October that after about 10 o'clock in the morning I am in close contact with the FOM Bureau, because 2 people in the FOM Bureau, Huub Eggen and Annemarie Segers, they are on alert, because at around 11 o'clock or so the Nobel Committee on Physics comes with the result, and you never know whether it ends up in the Netherlands. And then in half an hour it has to be on the FOM website, because I still remember Ad Lagendijk's column in the Volkskrant saying that when the Nobel Prize ended up in the Netherlands, Gerard and Tini, he had checked whether we had it there at about 12 o'clock. And if not, oh, but we had it. And I asked a question. Now, in 1997, I asked the question, my usual question, how old are they? Because somehow I have an unhappy feeling that when it is given to an octogenarian, someone in his 80s, I'm not sure it's good for the public image of physics. And the answer in 1979 was nearly 50. Well, that's exactly what you want, of course. You want a role model. You want to show the vitality of the field. A person around 50 receiving the Nobel Prize. That means that he's still among us, well, another 15, 20 years and he can influence the field. The Nobel Prize 1997, person nearly 50, Steve Chu. He is here. And of course, at that time, it was, and the common people will love it, for laser light to cool gases. But then, he moved fields. And the word biology entered, and the interface between physics and biology. And then, there was this combination of being a super outstanding scientist and management. Because he now runs a national laboratory. 3,800 persons. 500 million dollars, yearly budget. That's a different ballgame. And then also, and that's one of the reasons, of course, where we are honored that he accepted the invitation to come, the word energy. And of course we thought, that must be a role model, because Nobel laureate, come up community, so to speak, and suddenly the word energy appears in his mind, and we are very eager to hear what he is going to tell us about what's possible. Steve, may I invite you to give your presentation?
All right, thank you very much for the kind introduction, and it's a great pleasure that I am here to talk to you about something I care very much about. So I don't take too much of my successor's time, I will want to start on this. And so I really want to tell you about the world's energy problem and offer potential solutions. There are many solutions. So what is the energy problem? Well, I first got interested in the energy problem maybe 6 or 8 years ago because of a growing concern I had about climate change. And over the last 5 years, at least in my mind, it's stronger evidence that suggests that there could be very serious consequences in climate change. But I should also remind you that roughly 1/3 of the population of the world doesn't have access to modern forms of energy. 1.6 billion people don't have access to electricity. So by modern forms of energy, I mean that these people, 1/3 of the population, actually, this was designed for people who wear ties. You know, they go out and get twigs, and they burn dung and lumps of random coal that they can find. So this is of great concern. And then also there is great potential for geopolitical conflict as the escalating competition for energy increases the energy security that was mentioned by the previous speaker and so on. I know that 95%, maybe 99.9% of you know about the climate change, but I just want to briefly spend 2 minutes, 5 minutes on this, to remind you that the average temperature of the world is increasing. This is from 1860 to 2002, but 2003, 4, 5, and 7 are ever increasing. That there are some people in the world still who are not convinced that it's caused by humans, and so let me give you one piece of evidence that suggests it is. This is the measured amount of carbon dioxide, methane, and nitrous oxide in the atmosphere. And what happened when you see the sudden rise is that the world entered into an industrial revolution, the first industrial revolution, where we began to burn large amounts of coal and other fossil fuels. There's actually some radioactive dating that can even pinpoint this. I will hold it, but pinpoint even more, but it's safe to say that this increase in the greenhouse gases is due to humans burning fossil fuel. So you can try to make some correlation between the red line, which is the increase, measured increase in temperature, and climate models. In these climate models, you can put in, since they are computer models, you can put in variations that are known due to solar variations, volcanoes. Big volcanoes emit a lot of sulfur dioxide. It reflects sunlight and it has a cooling effect. And when you fold in what we know to be natural causes, you find that you can't really fit the model to the increased temperature rise. But if you fold in what I just showed you, the increase in greenhouse gases, then it becomes a reasonable fit. Now, is this proof that humans caused this temperature rise? Actually, to a hardcore scientist, it's not proof. It's just suggestive. But if you have a dozen things like this, then it begins to build a very strong case. So the IPCC in 1990 said there was no strong evidence that humans caused climate change, but in the latest report they said there's a greater than 90% probability that the bulk of the climate change was caused by humans. So it's mounting evidence of this nature in many different realms in science that are strongly suggestive that this is due to humans. So then let's look forward and let's talk about potential predictions. And so let me first, before I talk about some of the predictions, I have to caution you by quoting a very famous saying by the great American philosopher of the 20th century by the name of Yogi Berra. He said, he's a catcher for the New York Yankees, he played baseball, but he said many wise things. For example, he said, when you come to a fork in the road, take it. We're lost, but we're making good time. Or that restaurant no one goes to, it's too popular, no one goes there anymore. He said many wise things. He said predictions are hard to make, especially about the future. So there's a number of predictions. There's the prediction that disease will spread, especially diseases associated with temperature and water, like malaria, cholera, dengue fever, and we're beginning to see some of this. There's increased species extinction, so on and so forth. I'm only going to talk about two: water shortages and sea level rise, and what that could do in terms of the world population. So let's talk about water shortages. And I'll reference one paper, there are many. This happens to be from the Proceedings of the National Academy of Sciences, 2004, and it makes a study of what would happen locally. Locally is California, in two scenarios. B1 is a scenario where the carbon in the atmosphere in this century would be less than 500 parts per million. We're at 380 parts per million today. Before the Industrial Revolution, we were 275 parts per million. There's 420 parts per million carbon equivalent today. Most people, unfortunately, feel now that this is not attainable. We will go beyond this one. A1 is a business as usual scenario. In the most optimistic scenario, the alpine and subalpine forests that constitute the watershed, the primary watershed in California, will be half to 3/4 gone. And the Sierra snowpack will be 30 to 70% gone. And in the more pessimistic business as usual scenario, it's mostly gone. This is an example of a prediction in British Columbia, 78% of the pine forests are predicted to be dead within a decade due to pine beetle infestation. So here's the prediction again. This is a picture. The red is dead standing pine. The green is a live pine. This is a picture in British Columbia. Now you might say that I'm being an alarmist, that this is terrible and it's really not going to happen. But let me just quote something from the British Columbia Ministry of Forests and Range 2006. It's 40% gone today. 40% of the pine in British Columbia are now dead, according to the best government estimate, which is actually trying not to be alarmist. Okay? So what is happening? What happens is the winters are milder, they don't kill the parasites in British Columbia, and because of that, the pine beetles then ravage these lodgepole pines in British Columbia. This is also happening in California, it's happening in the Rocky Mountains, and it's in fact happening all over the world. Another thing that is happening all over the world is that the glaciers and snow-capped mountains are beginning to shrink rapidly. The Tibetan Glacier and the Himalayas, which serve about 1/3 of the population of the world in terms of a water supply. It's a slow leakage of this water over the steady stream of water. Its thickness is decreasing by more than 1.2 meters a year. This is 2005 data. And so if you look at Pakistan, India, Bangladesh, the other part of Pakistan, China, many of the biggest river basins in the world are fed by the Tibetan Plateau. Already in China, the Yellow River in the north is beginning to run dry due to a combination of reasons. Misuse of water, over-irrigation, increasing population, and climate change. And so now China is embarking on a massive project to bring the river from the Yangtze River to the Yellow River in a series of 3 aqueducts. California, for those of you know, California has a major aqueduct system that brings water from the North California to the south. Californians spend 20% of their electricity moving water, pumping water from wells or in the aqueduct system to get it over the mountains. And as the water supplies in the West continue to decrease, there are massive plans again to move water around, but it will require increasing amounts of energy, hence, you know, the way we do it now, increasing amounts of CO2, and so it's a very positive feedback. Let me tell you about another thing. The northern latitudes are warming up pretty rapidly. The 1979 to 2000 average of the snow in the Arctic Ocean in the month of September, where there's the biggest melting, was this orange line. And in 2007, this is the amount of snow we see. 2005 was, and 2006 was somewhere in between here. So the Arctic Ocean is melting very rapidly. When there's no snow, you get to absorb more sunlight, it heats up the water, and so the refreezing is slower, and so again, it's a positive feedback. Now, if the snow in the Arctic Ocean melts, the sea level will remain the same. It's a natural buoyancy effect, it's like ice cubes in water. But the worry is that as the northern hemisphere warms up, that will have an effect on big sheets of ice, for example, in Greenland. And so here's a picture of the ice sheet in Greenland. It too is melting faster than we thought 10 years ago. It's due to 2 reasons. One reason is that the snow is actually dirtier than we thought, and so the soot that is deposited in this absorbs more energy. And another reason is that as the snow melts in the summertime, you form these underground rivers that go down into the interface between the ice sheet and land, and this fluid actually acts as a lubricant. So even though the snow in Greenland is actually increasing, it runs off the continent faster. This is one of the most, or the fastest moving iceberg in Greenland, and in the last 10 years, the rate of flow of Jacobsen Glacier, this is what looks up close, but this is from a plane, has increased by a factor of 10. The current flow is 40 meters a day, so it gives a new meaning to glacial speed. And so as this ice runs off Greenland more rapidly, and the satellite images are showing there's more melt, it's this ice on land and also in Antarctica that will actually cause the sea level to rise. If you look at the last IPCC projection, you will find that the prediction is not that alarming unless you live in the Netherlands. It's going to be less than a meter in this century, according to this official prediction. However, in this prediction, they did not include what we call tipping points. And a tipping point would be, as the Earth warms up, there would be much more greenhouse gases emitted that were trapped in the Arctic regions, particularly in Russia and Canada, that trap methane and carbon dioxide. There's a lot of greenhouse gases in the frozen tundra. If this is released, it would be orders of magnitude more than what we put up per year as humans. If you get to this tipping point, then we enter into a really new phase. And at that point, the consensus is Greenland would melt. And if all of Greenland melts, there's a 7-meter sea level rise. Why wasn't this included in the IPCC report? Well, it was not included because it was regarded as uncertain. We don't really know at what temperature this will happen. Is it 3 degrees? Is it 4 degrees? Is it 6 degrees? We just don't know. And because of that, it was excluded. But there is a growing nervousness that it might be in the 3 to 6 degree range. And the Stern report, which was mentioned, the Stern Review report, says that in this century there's a 50% probability that we will go up to 6 degrees centigrade increase. This is a profound statement because most people don't realize that the difference between where we are today and the ice ages, the coldest part of the ice ages, was about 6 to 8 degrees centigrade. At that time, all of Canada, the United States down to Ohio, Pennsylvania, was covered in a sheet of ice all year round. I think the Netherlands might have also been covered in a sheet of ice all year round, but, okay. So 6 degrees, world average, is a profound change in the globe. So 6 degrees the other way, it would be an equally profound change. So I think most of the public doesn't realize how big 6 degrees is, because after all, you see this from day to night, summer to winter, it's much more than 6 degrees. Okay, but the world average, so I don't know how to convince the public that it's a bigger deal. Okay, what happens? This is an investment tip. This is where the beachfront property will be at 1.5 meters and 3.5 meters rise in sea level. This land is fairly inexpensive today. Bangladesh with a 3-meter rise in sea level would mean that perhaps a third or half the population would be permanently displaced. 3-meter rise in sea level would be not good for Netherlands as well. So when they're permanently displaced, where did they go? Well, many of them may have to go to India, but then there is huge political instability when very poor people just bodily walk over to India because there's nowhere else to go. Different culture, different religion, all sorts of things. So this, if this happens, there would be huge political instability. So this is a graph of the amount of wealth per person in various countries, and on the y-axis is the amount of CO2 emissions per person. So here is the United States leading the pack in wealth and also in carbon dioxide emission. This is European countries. Now, the United States has to go down, and there's a growing consensus, roughly speaking, that the world, the developed world, has to come down, well, the United States, let's say, has to come down by about a factor of 5. In fact, it's a pledge of the governor of California to reduce carbon emissions by mid-century by a factor of 5. I'm not sure we can get there, but that's the goal in California. Now, the real question, one of the most important questions is what will happen to the developing countries as the economies of China, India, and other developing economies increase. Will they follow the path of Australia, United States, Canada, and other countries? And when they get to this point, they say, oh, this is a terrible mistake. We have to build an infrastructure that's more energy efficient and come down here. And the United States will have problems because they have big sprawling cities and not good habits. Or can we convince the developing countries in their own economic benefit to take a better curve? Within the next decade, or certainly within the next 2 decades, the developing countries will be about 60% of greenhouse emissions. So the United States, I believe, should lead the way. We're not. Europe is leading the way. But it also means we have to find some economic mechanism to allow the developing countries to develop along this path as well. So what we need to do is we need to maximize energy efficiency and decrease our waste of energy. And for the next 20, 30 years, this remains the lowest hanging fruit. This is the easiest thing to do. This is where the current technologies can be put to bear, and yet we're still not doing this. But we can't conserve our way out of this problem. We also have to develop newer sources of carbon neutral energy, and ones that were compatible, and how much society is willing to pay for energy. It cannot be a free market solution. If you allow the free market to try to find a solution, it will probably, not only probably, I will go stick my neck out and say it will definitely fail. Because there is a commons problem. What's a commons problem? You have a shared resource. It could be water in a river. And if you're upstream and your city upstream, you can dump sewage in the river, and it's much cheaper to dump sewage in the river so you don't have to treat the sewage. And no technology will ever make it as inexpensive. Now, if you're downstream, this is bad news. It costs a lot more money to clean it up, or if you don't clean it up, it costs a lot more money in terms of health, social, economic, agriculture, you name it, it's very costly. So this is a commons problem because both cities share this common resource. International fishing, another commons problem. If many countries share this international resource and you can't come to a sensible agreement, there's a huge temptation to take your fair share, and maybe epsilon more than your fair share. And what happens is that you have many areas in the world that are overfished. The population is not sustainable. It actually gets depleted. There are many areas around the world where the fishing industry has died because of overfishing. Climate change is the commons problem because it involves the whole globe, and it's where many players feel, well, it's maybe we care about it, but what can we do? So why not be focused on economic prosperity? You need a combination of incentives in private industry and fiscal policies and regulations. And above all, you need a worldwide price on carbon. But it has to be stable. And so what I mean by that is right now, and Europe is learning, the United States has a toy market, it's not real, but it goes up and down. And in order to encourage investment over a long period of time, 5, 10, 15 years, what industry is most scared of is the price of oil, which is now hovering around $100 a barrel, might go down to $40 a barrel or $50 a barrel. And if it does that, there are many industries that could get wiped out. So somehow we need a price signal that slowly increases over a 10, 15-year period, but to say with certainty in 10, 15 years, it could be $30 a ton, $50 a ton, okay? And that the government will step in and make sure that it doesn't ever sink down to wipe out emerging industries. This is the most important thing we can do. But regulation is also important, and let me say that in the first oil crisis in the mid-70s, there was things that happened. It was actually, this was led actually by a Lawrence Berkeley National Lab physicist, Enrico Fermi's last student, Art Rosenfeld, who then took the laboratory and the University of California and the state of California into being very conscious about it, how it used energy. And since that time, the electricity use per person in California has remained roughly constant. The rest of the United States, excluding California, has gone up by 60%. The economy in California has grown more rapidly than the rest of the United States, which is a proof that being energy conserving doesn't kill the economy, but yet in most of the United States, this is not appreciated. It was a combination of higher insulation and building standards, better appliance standards in refrigerators, air conditioning, heating, in separating out the profit motive from utility companies so that every time a utility company in California would preach energy conservation, they could pass those costs on to the consumer. And they became the biggest advocates for energy conservation, because if more energy was conserved and if it was spread out over the full day instead of just in the, let's say, peak summer hot months, they could build less power plants, hence less capital investment, hence more profit. Let me give you an example of what happened in California. This is actually an example where Art Rosenfeld went into an appliance store and he noticed in the middle 70s that refrigerators were varying in efficiency by more than a factor of 4 or 5, and yet for the same size refrigerator, there was little difference in cost because of a very competitive market. So without being a refrigerator expert, he could say, energy efficiency has nothing to do with the cost of a refrigerator. Why don't we increase the standards of efficiency, because the consumer doesn't really apply enough direct pressure to manufacturers of refrigerators. Now, at the beginning, the refrigerator manufacturers complained bitterly. They tried to fight this with lobbyists, with all sorts of lawyers, and for a while, they stalled progress. But eventually, in California, both the Republicans and the Democrats said, this is a good thing to do. And so what happened was, as soon as the lobbyists and lawyers were out of business and they assigned it to the engineers, progress was made. Now, the first refrigerator standard started in 1978, but yet the efficiency has decreased from this peak till 2006. It's decreased by about a factor of 4.5. But you might ask, why did efficiency start to increase even before the first standard appeared? Because the way the law was written, industry was given fair warning. This standard will appear a few years from now. Think about it. And by the way, in another few years, a higher standard will apply. Think about it. So what happened was a tremendous savings in energy. The size of the refrigerator went from an average, this is energy per refrigerator, the size went from 18 cubic feet to 22 cubic feet. Now you might say, my gosh, even the appetite of Americans is being saturated. No. It's asymptotically approaching this level because of the size of the kitchen door. The refrigerators are getting wider and the same thickness. It's amazing. The cost of the refrigerators in inflation-adjusted price went down by a factor of 2. So what industry was complaining about never happened. Okay? And this is repeated over and over and over again. They say first, it's not going to work, the American consumer can't pay for it, et cetera, et cetera, et cetera. But once they start thinking about it, miraculously, the engineers are quite good. All right. So insulation, lighting, building efficiencies. In the United States, 40% of our energy is spent in buildings. And the architects tell me that a factor of 2 is possible and it could save money over the life cycle of the building. The payback time would be 5-6 years. And a building that might last 50 years or 80 years. You know, in Europe, they last hundreds of years, but in the United States, not so long. But nevertheless, these investments are not being made because when you build a building, you don't run the building, and so there have to be financial mechanisms to allow this investment to be made. Now, I can talk about many, many things on the supply side of energy, but I can't, I don't have enough time, so I will focus on just two: solar photovoltaic and biomass, not because I think these will save the world. I think we need improvements in all of these areas to save the world, but I'm going to focus on these two for two reasons. It's because science is very rapidly developing in these two areas, and it also has something to do with the laboratory that I'm part of. So let me put in a little advertisement for Lawrence Berkeley National Laboratory. For those of you who don't know, it's on a site overlooking the Berkeley campus. It's not to be confused with Lawrence Livermore Laboratory. We do absolutely no classified work in the entire laboratory. It's mostly a basic research energy or basic research science laboratory. It's the oldest of the national laboratories. 11 of its employees were awarded the Nobel Prize. 9 of them did their work at the laboratory, but what's much more important is that if you include the graduate students, postdoc, and young scientists that were actually trained there, the number goes to 55. And so this is a record that very few research institutions around the world, maybe 10, could boast of. I was trained at University of California, Berkeley, but I was also a graduate student and a postdoc at Lawrence Berkeley National Laboratory. And today we have 3% of the membership of the National Academy of Sciences in America in this laboratory. When I took this job 3.5 years ago, a major reason why I took the job is because I thought if I could interest the caliber of scientists who work at the laboratory and who work at the University of California, Berkeley, then we could help in a significant way in helping solve the energy problem. For the last 30 years, the laboratory has been a pioneer in energy efficiency, but also to actually do this in the supply side of energy. And so we looked around and decided that, of course, on the long term, you want to harness as much of the sun's energy as possible. And so there are many pathways in order to get there. You can generate electricity via photovoltaics, solar thermal. We have to address the energy storage problem. We also have to address the transportation fuel problem. Now, if you think about where the energy is going to come from, for example, if you want to think about biofuels, and you look at the globe, you find that in these blue areas, there's not enough, it's not warm enough, and especially in Mercator projection, there's a lot of frozen stuff. The red means there's enough warmth, enough sunlight, but not enough water. So this is desert for the most part. Black is good. Black means there's enough sunlight and you can grow things, enough rainfall. So the first thing you're struck with if you get the right perspective is that most of the world is desert. So you are immediately thrown into thinking about solar energy to generate electricity directly via thermal processes in which you reflect the sun's rays and you make this is a type of steam engine, if you will. This is another type where you heat up salts in a fluid that then run a steam turbine or photovoltaics. Right now, the cost of photovoltaics is such that you will not get people, ordinary citizens, putting them on your rooftops or businesses putting them on flat top roofs of buildings without a subsidy unless there's a factor of 3 reduction. This is numbers in the United States, a factor of 3 reduction in the cost of generation of this electricity. Solar thermal is actually more efficient by about a factor of 3, but still it's Utility companies won't do this without subsidy. And you need a factor of 10 in photovoltaics before a utility company will start putting these things in the desert for commercial generation. Now, that's actually not that far away, and to whet the appetite of the young people in this audience, you saw a desert. At 20% efficiency, which is available today, you would need 2 to 3/10 of the deserts of the world to generate the current electricity needs. So that going into the future and considering that you would have to have an overcapacity, we're talking about 1%, 2% of the world's desert, which is inexpensive land, to generate the world's electricity. So it's sitting there. We just need better ideas on how to make it less expensive. The current learning curve, this is plotted the cumulative megawatts that are installed. So this is actually being deployed, and as more things get installed, the prices go down. This is a logarithmic curve. When you see a straight line, it means you're getting exponential improvement, not at the speed of Moore's law for semiconductors, but every technology has a Moore's law curve, it turns out. Photovoltaics, after several decades, has established a Moore's law curve based on current technology. And we're about a factor of 10 away from fossil fuel. So if you want to extrapolate that, you can say, oh, simple. We just put in more subsidies, you get more installed photovoltaic, it'll cure the problem. Not so simple. Because if you over-subsidize, the incremental steady improvements that occur over time are taken away, and then you start stamping out the current technology, and then what you generate is a shortage of silicon. So there's a temporary shortage of silicon, which means the cost of photovoltaics is burped up a little. Then people will, produce more silicon photovoltaic. That's good. But if you stay with that technology, you're still going to make steady incremental progress. So what you really need, if you want to get to where you want to go, which is down here somewhere, is you need a breakthrough. And so if you take all these technologies, this is where these predictions that I've told you are coming from. You just look at the learning curves, you look at what's invested. The only way you fall off the learning curve is you saturate or you over-subsidize. The other way you fall off the learning curve is to go on a new slope, a new intercept with a new technology. What are some new technologies? Well, this is the sun spectra that reaches the Earth, and you can take the very high energy photons and you can use certain semiconductor material that captures that high energy and uses that to convert to electricity, and you can divide the solar spectrum into different bands. Each band wastes as little of the photon energy as possible. The current efficiency is about 40%. It can be over 50%, but these things are very, very expensive, so what you need is a solar concentrator to collect the sun and put it on this little, essentially, chip. So that is one possibility. It might work, it might not work. I'm just throwing this out. Another possibility is you make single band gap material, very inexpensive, the way you would print plastic or newspaper. And then you would use new materials, thin film technology, possibly nanotechnology. Let me give you one example that we're looking at. We have maybe half a dozen ideas that we're now exploring. This is a material of copper, indium, and selenium. It's of scale 50, 100 nanometers in length. It is essentially a large molecule, if you will, a nanoparticle, which automatically, if the sunlight goes into it, it separates the charge into electrons and holes. And it's conducted, the electron and hole is conducted to the other side of the nanoparticle. The problem is actually making particles like this is not a problem. Making them absorb in the right spectrum is not a problem. Separating the charge is not a problem. The big problem is how do you make good contact, electrical contact with two electrodes? And how do you get them all to line up? And so one way is these things are natural electric dipoles. An electric field can line them up, and then you want to compact them, and so on and so forth. So this is a thing we don't know how to do yet, but it gives hope that you can mass produce these things using wet chemistry, thin film technology. So mentioned by the previous speaker, energy storage is an unsolved problem. There's large-scale storage of transient sources of energy like solar, photovoltaic, or thermal, or wind. And there's smaller scale for the isolated villages in developing countries, in communities, buildings, homes, and of course, most important, the laptop computer. So let me tell you a little short story about energy storage. In 1991, the Department of Energy and U.S. auto manufacturers had a glimpse of a breakthrough using not silicon ion batteries, but where the electrode is a solid piece of silicon metal. There was a new polymer that can conduct the ions across, and all of a sudden one realized this is again a logarithmic curve, that you could double the energy density and the peak current, although the peak current is not a problem with lithium ion in for example, automobiles. The Tesla automobile, which some of you may have heard of, or probably no one in this audience has put in an order for one. They're about $120,000, 0 to 60 in less than 4 seconds. It's an old battery vehicle, but the batteries are Sony computer batteries. I'm not sure what the warranty is, but for $120,000, maybe you don't care. In any case, this was a goal of the Department of Energy to use this exciting new electrolyte, polyethylene oxide, and 8-9 years later, the program was canceled. Why was the program canceled? It was because you have a metal anode, you have a cathode. In those days, it was a cobalt phosphate. And then you have this polymer electrolyte. And if you start to cycle the battery, because the polymer had to be flexible, because it was an inherent property of the polymer, of its flexibility to allow the lithium ions to go from the metal anode to the cathode, it would get rougher, and then some dendrites would form, and it would short out. And after a bunch of years, there was no technological cure for this, so the program was canceled. The electric vehicles that were thought to be deliverable in the mid-90s were stopped. So the solution, or the potential solution, is a hybrid solution, just like the hybrid car is a hybrid solution. And the hybrid solution in this case was that this magical polymer that was very flexible, but its flexibility allowed it so that it would make a little crack and it would short out. But what you needed was a polymer with huge surface tension, so that if a crack started, the surface tension at a nano level would just flatten it out. Just like you won't, a nascent bubble might implode because of the surface tension. So a scientist, Nitesh Balstra at Lawrence Berkeley Lab, said, why don't we combine the two properties we want? This PO in blue, which is very flexible, but it doesn't have the right material characteristics, but it was a good conductor, with a very rigid polymer, polystyrene, which is the fundamental ingredient in football helmets. Okay? Just make polymers like this. You throw them into a soup. They actually, this is a microscope picture. This is the size scale, 100 nanometers. Every 20 to 50 to 80 nanometers, the dark stripes are the conducting polymer, the light stripes are the football helmet stuff. Now, you notice that they're not perfect, so they're interleaved. So the electrons and the lithium especially, the lithium ions can run around this dark stuff and find cracks and crevices, and the conductivity is only a factor 2 worse, but that was irrelevant because it was such good conductivity it didn't matter. And yet, the surface tension of the hard stuff prevented the dendrites from forming. How well did this work? Pretty good. The latest results are this battery has been cycled 1,000 times in deep discharge, 90 to 10%, no sign of wear. Actually, no sign of wear after 1,000 cycles means probably no sign of wear in 5,000 cycles. You actually only need about 3,000 cycles to last 10 years. This is an earlier result where it was 100 cycles. So, oh, by the way, the Prius battery, the battery in metal hydride cars, is kept between 40 and 60% of charge. Because if you did deep discharge, it would act exactly like a computer battery, which is slightly different. It would begin to lose capacity in 1 or 2 years. So this, if this maintains itself and you can make a commercial product, it's actually 15 times better than the commercial batteries we have today, which would be enough for making a plug-in hybrid or maybe an all-electric vehicle. So it was actually a small-scale research that led to a breakthrough. And I emphasize this to any funders. You know, you can throw a lot of money in a big-scale thing, but actually it required a new idea. So let me go to biofuel production. Here the idea is you capture sunlight, you make some biomass, you turn this biomass in the form of woody material or sugars and starches and other things, but in this case I'm concentrating on leaves and stems and stalks and things like that. And you can break it down into simple sugars and then you ferment them into ethanol. You can improve this in many ways. You can develop, as people are trying to do, algae that directly converts sunlight into a fuel like a diesel fuel. You can take the biomass and you can actually gasify it into a mixture of carbon monoxide and hydrogen, and then you can use chemical processes to convert it into a fuel. Or you can take this and simplify this process. So we are looking at all these ways of doing it. You might ask, how can you be talking about biomass because you know, we need to eat food, and is there actually enough arable land to grow both food and energy? Well, yes and no. Yes, if you do it correctly. Now this is what happened from 1960 to 2005. In 1960, the population was 3 billion people. In 1960, many people thought that the world was inexorably leading to a disaster, that there's no way you can feed all the people in the world. What happened is the so-called Green Revolution. Norman Borlaug got a Nobel Prize for his work on dwarf wheat, which was also disease resistant. This is what happened to the yield and productivity of grains around the world. This is the amount of land used to grow the food. So it's roughly flat, but the yield increased fourfold. So that prevented mass starvations that were predicted in the 50s and 60s. But I meant yes and no, because growing food crops like corn or rapeseed for biofuels actually is not the right solution. The yield is too low, it requires too much fertilizer, energy investments, and it just, well, it's just plain dumb. Because it's heavily agricultural intensive, and things like corn actually cause a lot of soil erosion. And so let me give you an example of something that is better. This is a grass that grows in the wild in Asia, it grows in the wild in the United States. It's called miscanthus. This is a graduate student of one of our collaborators, Stephen Long, from the University of Illinois. She's 5'4", in case you're interested. There's another picture of a basketball player, but it was decided this would look more impressive. But in any case, the year before, this grass was mowed down, and this is what grew without irrigation and without fertilizer. It's a very rapidly growing weed. And the yield of this unfertilized, unirrigated plot of land in Illinois was 15 times more per acre than ethanol. And if you look at all the agricultural waste like wheat straw, corn stover, some fraction of the corn stover, urban waste, animal manure, all these things, in the United States, which has huge agricultural capacity, the estimates are half or perhaps all of current US consumption of gasoline, which is about 2/3 of transportation fuel. The other third is airplane fuel, diesel fuel. The perennials are better because you don't have to plow the land for 10, 15 years. They grow up year after year. The roots actually fix their own nitrogen, so you're relieved. That's why they do well without fertilizer. You do need to supply other types of nutrients. But many of these nutrients are actually conserved in the plant. In harvest time, the plant actually brings them back down into the roots. So when you chop off the top part, the plant has, you know, it's autumn time. I want to be back another year, so the plant stores some valuable nutrients. And in a grass like switchgrass, which is not as good as miscanthus, it's 1/8 the nitrogen runoff and 1/100th the soil erosion of corn. So this is a preferred way to grow biofuels, not the crops we now grow for food. So why aren't we doing this today? Because today the green bars reflect the cost of turning sugar beet into ethanol, or Brazilian sugarcane or US corn, and the only thing that actually makes sense now, corn has gone up because it's now heavily subsidized for biofuels, is Brazilian sugarcane. The rest, quite frankly, don't make any sense. And you need to bring down the cost of these technologies by about a factor of 2 or 3. Quite frankly, sugar beet is probably never going to make it, because if you look at the possibility of what these plants can yield, it doesn't look promising. The grass that I just showed you was an unimproved grass, meaning that we don't use breeding or any other means to make the yield bigger. In the United States, breeding corn, not genetic modification, just breeding, increased the yield per acre by a factor of 7 since 1930. That plus fertilizer plus irrigation. So conservatively, we should expect a factor of 2 yield in the grass by breeding, but you still have to bring the cost of converting the cellulose into a biofuel down by roughly a factor of 3 or 2.5. This is the goal of some of the research we're doing, and we just received a grant or a contract, if you will, for $50 million a year for 10 years from BP, University of California, Berkeley, Lawrence Berkeley National Lab, and University of Illinois to do some research in making this truly economically viable. We just received a grant from the Department of Energy at half the rate, $25 million a year for 5 years, but we expect this to continue for at least 10 years, and the Lawrence Berkeley National Lab is the lead in this. What do we want to do? Well, the biggest cost of converting cellulose into energy is the fact that the cellulose are long strands of complex sugars, long polymer chains of sugars, and you have to first separate the cellulose from this protective molecule, set of molecules called lignin, and then you have to break down these long strands of sugars into simple sugars, where you can use a 5,000-year-old technology called fermentation to make ethanol. The most expensive part of this process is the reduction of the long polymer chains in this cartoon. This is a long polymer chain of sugar. This is a molecule that actually chops up these long polymer chains into simple sugars. Over 15 years, the Department of Energy has been working with 2 companies, Genicor and Novozymes. Actually, I think at least one is based in Europe. And they've achieved a factor of 20 to 30 reduction in the cost of breaking down complex sugars into simple sugars. And they found that a cocktail of 3 different enzymes were to work more efficiently, but you still need a factor of 2 or 3 before it's really commercially viable. So, if you use 3 different enzymes to break down the sugars because they kind of work in cohort together, you can now begin to think of, well, not use the enzymes. Where do we get the enzymes? We get them from growing microbes, growing up the microbes, killing microbes, extracting this molecule, the enzyme, and sprinkling on the cellulose. There are actually organisms that have the enzymes built into it that self-reproduce. So the question is, can we generate an organism that has a mixture of the right enzymes? Just like a single drug that fights AIDS is not as good as 3 drugs that fight AIDS. And so some of us are thinking of ways of taking these various enzymes, putting it on a bug that self-reproduces, so it really is voracious about gobbling up the things, and oh, by the way, it reproduces itself. And already there's a factor of 2 to 4, close to 5-fold better rate of chewing up the cellulose than in these enzyme preparations. But again, it's still experimental. It's not commercial scale. It's still in a laboratory. Here's another way of breaking it. This is a cartoon of a termite looking beetily at a house. And when a termite eats your house, it actually can't digest the wood. It can eat it, but if you ate wood, you would feel full for a little while, but after a few hours you'd feel hungry. Kind of like Chinese food. And I'm allowed to say that. No one else is allowed to say that. So what the termite has done is it's developed a relationship with bacteria in its stomach. These are several stomachs of a termite. And in the stomachs of these termites, there are actually dozens to as many as 100 different bacteria that work in concert, like the many enzymes, to break down the cellulose into fuel. They take a little bit of the energy for themselves, but they actually miraculously pass most of it on to the termite with instructions, feed me, go get another house. So the termite and the bacteria are very happy. And so what we're doing is we've entered into partnerships with companies that go prospecting for termites all over the world. And we then sequence the genomes of these termites, and we're trying to find out, not the genome of the termite, we're not interested in the termite, the genomes of the microbes in the stomachs of a termite to find out how they really work. And can we, again, develop a better set of microbes that could digest the wood faster with the instructions, you know, here's most of the energy, feed me more cellulose. So that's another area of research we're working on. Now, this might sound like science fiction, but it's not. Because what we're talking about is taking a microbe, like in this case an E. coli, inserting dozens of genes into the microbe in order to transform it into a little chemical factory of what we want. And this could be the microbe that breaks down the cellulose. It could be the microbe that converts sunlight into an oil, like in an algae, directly. It could be the microbe that forgets about ethanol and yeast, but actually takes cellulose and converts it into a better fuel. Ethanol is not ultimately a very good fuel. It's low density, it mixes with water. You know, we'd rather have a microbe pass methane, pass gas like methane, or even better still, you know, pass out diesel fuel, which actually bubbles to the top. So it self-separates. Whereas yeast, after 5% alcohol, begins to slow down. After 14% alcohol, the alcohol kills the yeast. So, you know, anyway, in this case, Jay Kiesling, a member of our laboratory who's now director of the biophysics science division, has inserted 24 genes into an E. coli to create a new anti-malarial drug. He's handed this off officially to industry. The industry and Jay Kiesling were given a $42 million grant from the Gates Foundation to commercialize 6 years ago what was the gleam in his eye as a potential cure for malaria. We're on schedule, ahead of schedule actually, and we hope in 1908 or early 1909, this will be delivered to the third world countries at 20 cents a cure. So the idea here is this company that was started, which had to pass on the intellectual property at cost, was allowed to keep any intellectual property for anything else, and it turns out that this drug is a close relative of a fuel, and it's now beginning to look at producing fuels. Since it's gone in this direction, and since Jay Kiesling wants to do some more research to look at other opportunities, even though he was the founder of the company doesn't talk to him anymore about what they're doing commercially, but that's okay, because he's now going to look at a separate avenue, again, for maybe even better hope. In the end, we want to get away from algae, we want to get away from plants, because all these things use a tremendous amount of water, and the world doesn't have enough water for satisfying the world's transportation needs. So what you want is artificial photosynthesis that's much more thrifty with its use of water. You could look to nature just the way Leonardo da Vinci looked at nature and the way birds flew, and would invent some contraption. You strap this on, you jump off a cliff, you hope for the best. The first thing that flew by powered flight didn't look like this. It didn't look like a bird. It was a hybrid solution. The wings and the control of flight was due to wing warping, where here you see the plane edge on, where the wings are actually warping. There was no vertical tail, which is very hard for a bird to make. It might look ugly. It could interfere with mating if you had a vertical tail. And so it's a horizontal tail. And if you look at the way a bird flies, the horizontal tail does a lot of gyrations like this, and the wings do a lot of gyrations like this. The engine had nothing to do with the bird. It was a gasoline engine. If you look at today's 747s, there's a vertical tail. The jet engines, turbines are made of single crystal blades of metal. The vertical tail might get in the way of mating. But in any case, the 747s work a lot better than birds for what we want to use them for, hauling ourselves around and other things. So it's this example that says we can actually do better than nature. So what does nature do? It takes water and it turns water into hydrogen and oxygen across a boundary. It takes carbon dioxide out of the atmosphere and turns it into carbon monoxide. And with these ingredients of hydrogen, oxygen, and carbon monoxide, it begins to assemble a chemical form of energy in the form of a carbohydrate. Maybe we can do much better than a plant or an algae. And maybe we can, because we're lifted from the constraint of materials that have to self-reproduce and have to work in wet. It could be at some level it has to work in wet, but a lot of these things inside here could be refractory materials. That's another one of our research areas. This is again a picture of Lawrence Berkeley Lab. We're assembling, going around trying to get people excited about it, also trying to get people excited about funding us. So this is the beginning of our funding attempts, both on a commercial level with BP and Department of Energy level. This is for solar photovoltaics and catalysis. We've got the state of California to invest in us. The University of California, for the first time since E.O. Lawrence, has decided to invest in us. We've gathered $20 million in donations for the building and so on and so forth. The building has cost overruns, so people say, Steve, go find another 20 million. So in case any of you want to talk, I'm here. And we're also talking with private foundations. We're also forming industrial partnerships, not only with BP, but with other companies, big and small. Not only for a grant. Now the BP grant is actually pretty good because the stuff, it's good not for the amount of money, it's also good intellectually. The discoveries we make will be openly published. If it was invented by UC Berkeley or LBNL or University of Illinois, it will be openly published. It will be owned by those institutions, then licensed to BP. So that's pretty good. We are trying to establish other relationships with corporations that would be know-how, specialized, business sorts of things. And so more and more companies are now becoming, they're actually knocking on our door, which is a very nice thing in the last year and a half, and say, we want to work with you. United Technologies has approached us, we did not approach them, and said, in energy efficiency, we want to work with you on pre-commercialization things that could be openly publishable. To increase energy efficiency technologies. United Applied Materials, a $50 billion company, has approached us. Dow now has a sciences in residence. It's another $50 billion a year company, $50 billion a year sales, and so on and so forth. So So this is also part of what we're trying to do. But it's not only about money. And I want to tell you, we also want to start to change the culture of the way we do things. This is a picture of Ernest Lawrence, the founder of Lawrence Berkeley Lab, surrounded by a bunch of scientists. Serber, Alvarez, Macmillan all got Nobel Prizes. Seaborg is not shown in this picture, also a Nobel Prize. That was part of a single team of scientists. Oppenheimer, whom you've heard of, also part of this team. So what Lawrence gave us, in addition to the invention of the cyclotron, was a new concept that teams of brilliant scientists, even though they're prima donnas in their own right, can actually work coherently in a team and do something far greater than an individual scientist or group can do. This has continued in Lawrence Berkeley Lab. The 2006 Nobel Prize was shared between George Smoot, who started life as a postdoc at LBNL. He led a team of scientists that covered one part of a mission, a satellite mission. Another team of scientists was led by John Mather at Goddard, who was trained at LBNL. They shared the Nobel Prize. George Smoot became leader of the team at the age of 32. Sol Perlmutter, who was a co-discoverer of dark energy, who probably will get a Nobel Prize within 4 or 5 years, was also a leader of a team. This is what he discovered was after the Big Bang, as the universe expanded, all matter and energy attracts one another. So he set about to measure how much the universe was slowing down after the Big Bang, and he got the wrong sign. He found it was accelerating. And this was confirmed. It's now understood to be about 70% of the stuff of the universe, although it's no form of matter and energy we know about. So it's a big deal. He called it dark energy because the work was supported by the Department of Energy. Maybe not. Again, he was a leader of this team at the early 30s, even though the team included members of the National Academy of Sciences who were in their 50s and 60s. So institutionally, we had a way of recognizing young talent and putting them actually in charge of big teams. Bell Laboratories was another institution I'm very proud of to be a member of. I used to live right here, hop over the fence, walk to work. It was actually the most enjoyable time in my scientific career in terms of what I learned there. This is what I looked like in 32 before the phase transition. This is members of a class of 77, 78, maybe 76. There were 40 of us who were hired within a 3-year period, all young people, all fresh out of graduate school or as postdocs. There were no established scientists that were hired at Bell Laboratories. For many, many decades, they only hired young people and they grew them. 5 of those people got the Nobel Prize. Over half of the people that were hired in the basic research areas at Bell Laboratories are members of the National Academy of Sciences. It's not only that they chose people well, they actually nurtured them, and we nurtured each other. And you work on many things at Bell Laboratories, not all of it basic research. Just in case you don't know, for the few biologists in the audience, this is the first transistor. It's something only a mother could love. This is the inventors of the transistor who got the Nobel Prize. This is Shockley, Bardeen, Bertin. These 2 guys, this one, Bardeen and Shockley, were theorists. This was the experimentalist. The only reason Shockley is pretending to do an experiment was he was the department head. But the progress in the transistor was not just these 3 people. It was teams of scientists who worked on all the other stuff that needed to be done. In material science, then there was many, many things that had to be done, and so many small teams of scientists started working on various aspects of the problem. And in the first 10 years before the discovery of the transistor, which was not accidental, by the way, it was very targeted. Bell Labs, AT&T said, we need to invent something that would replace the vacuum tube because the vacuum tube was not scaling in terms of reliability, in terms of complexity, and we needed a condensed matter vacuum tube, a solid-state vacuum tube. And so in the 9 years after Bell Labs scientists discovered if you put two semiconductors together and electricity went in only one direction, once you have that, just like you have a hot metal wire, electrons come out and you can collect the electrons go in one direction. They said you can put something in between that can modulate the electron current. So as soon as they discovered the diode, they said, we may be able to make a solid-state vacuum tube that would be much better. And boom, they started going off in this direction. It was not an accident. In those first 9 years and the following 10, 15 years, the foundations of semiconductor physics were laid, and there was a lot of beautiful science that came out of it. If you look at what Bell Laboratories discovered, the transistors, solar cells, molecular beam epitaxy, light-emitting diodes, the quantum demonstration of that matters had waves, the laser, the helium neon laser, the CO2 laser, the YAG laser. It was for communications that we discovered, but Carl Jansky discovered that Jupiter was emitting radio signals. And it was the 3-degree blackbody radiation that was discovered because they were looking for quieter signals. Now, they actually were also looking for astronomical signals by this time. And in much more down-to-home stuff, in information theory, electronic noise, energy transmission, the names Nyquist, Shannon, Johnson noise, Tukey for fast Fourier transforms. 80 years, this stuff was going on, and many, many more names. There was something magical that was going on. And if you look at Bell Laboratories, you look at the MRC in England that gave us DNA structures and the structures of proteins, Cambridge, England, and you look at a number of places of golden eras in science that lasted not 10 years or 20 years, but 50 years or 80 years. There was something common going on. Individual genius was nurtured, especially early in their careers, but they were encouraged, if you got a good idea, go form a team and we'll back you. Well, how do you know what to back? Well, you can't know what to back by peer review at a national level. It's just too cumbersome. It takes a year or two. This is not the way it works. At Bell Laboratories, if I had an idea, I'd go to my supervisor. They'd say, okay, let's go to the blackboard. We talk about it. When I became a department head, I did the same thing. Sometimes that very hour, I'd said, not a good idea. This is why I think it's not a good idea. They would go back. They could come back and tell me why I was wrong. And you enter into a scientific discussion, not asking anonymous referees who knew nothing about the person whether to invest in that person. So you need to direct the science by top scientists with an intimate knowledge, expert knowledge of the science. And when you do that, you can actually encourage bold approaches. You have a proposal, you can get, you don't have to work on this. I was working on a surface science experiment for about a year, and I said, I have a good idea that could cool atoms. And so I went to my, I was a department head at the time, I went to my director and said, I think I have a good idea. He said, well, we tried this before. It's probably not going to work, but okay, you can do it. Don't try to convince anyone else to work on it with you. Especially the people who had spent 5, 6 years working on it before. So I said, okay. After about 6 or 8 months, it looked like it was going to work for sure, so I quietly told them, hey guys, come on board. 10 years after the initial idea, I sat down to write the first draft of the optical molasses paper for laser cooling. You can go much faster in a setting like this. And so this is what we want to do in energy research. So let me close. And I apologize to the fusion people, but you just, you give them 20 more minutes. I want to quote two of my favorite authors. One is William Faulkner, who said at the Nobel banquet in Stockholm, I believe that man will not merely endure, he will prevail. He is immortal, not because he alone among creatures has an inexhaustible voice, but because he has a soul, a spirit capable of compassion and sacrifice and endurance. And those are the qualities we actually need to solve this energy problem. And with these virtues, the world can and will prevail over this great energy challenge. So this is said by me and Jose Goldenberg. co-chairs of the preface that was mentioned before, a body that represents over 150 academies of science around the world toward a sustainable energy future. And so I want to close with this image, a very famous image taken in 1968. Many of you weren't born. This is the first Apollo mission that went around the far side of the moon, and when the Apollo capsule came around, it saw Earth rise. And so what you see rising above a very bleak horizon of the moon, something that far away looks quite beautiful, and quite frankly, even close up, there's many places that look quite beautiful. But I want you to focus on two things. This is a nice place to live. This is not a good place to live. There's nothing else. Thank you.
It's impressive. And I think there would be a question session. But my suggestion is have the fusion people first and then half an hour question session.
Sure. Absolutely.
Yeah? Okay, I'll organize this. I'm going to improvise.
That's this.
Oh, this is one? Okay.
That's it.
Ladies and gentlemen, I think that was a very inspiring and thought-provoking presentation. And therefore, I'm now going to improvise a little bit, hoping that the organizers, and I'm also thinking of Mark and Annemarie, somehow can help me. Because there are about 1,100, 1,200 people here, and I have a lot of questions, and I'm sure a lot of you have questions. And it is impossible now to organize a question session. That's clear. And beside that, we still have a very interesting topic, and that is fusion and the Fusion Roadshow. Now, what I'm going to ask Annemarie is the following. Would it be possible that you go around there and find a room where after Niek Lopes Cardozo's his presentation, Steve is willing to deal with questions for 30 minutes? Oh, okay. And the reason, of course, why I am stressing this is you probably feel the urge of asking questions. And there's also something else. This lecture is so inspiring that instead of settling all these words, I think I pay my respect by organizing this question session, having in mind that the month of February is probably very important for quite a number of people in this audience. Because in February, you have to think about what kind of program proposal am I going to write for the FOM organization. This type of thing. And in February, the more experienced investigators have to consider whether they are going to apply for this very important European Research Council grant. And I can very well imagine that Steve's presentation just how provokes you with some kind of ideas. So I hope that Annemarie is now going to look whether there is a place where we continue with the question session. Because suddenly at a certain moment this evening there will be music, there will be dancing, but there still are the questions. And I'm now going to move to the last part of this program, and that is the Fusion Roadshow. Now, Niek Lopes Cardozo is one of the key persons in the FOM organization. In terms of the European Fusion jargon, he is the head of a research unit. But next to that, he enjoys giving theater performances, and he is also very good in giving music performances. He has thought about how to present the Fusion Roadshow to Fusion to the general public, and therefore also outreach is one of his specialties. Niek, may I invite you to present together with Mark Westra the Fusion Roadshow?
Well, ladies and gentlemen, thank you very much for being here tonight. It's my great honor to present the last lecture of today. We should like to start with this image. Maybe I should like to ask you to look at this for a minute while I take off my jacket. And roll up my sleeves. Somehow this image always makes me very angry and very active. It makes me angry because we've seen this coming for half a century or so, and we did nothing to prevent it. And it makes me active because it's time to act. The good news is that this is a challenge, as we have heard today, and it's a challenge for us scientists in particular. Well, we have got to stop those counters. And at the same time, we have to make more energy. You may ask, why do we have to make more energy? Well, it's become clear tonight because there's more people and they want to improve their standard of living. Can't we get there with energy saving? Well, let's have a look at the next picture. So there's a relation between wealth and energy use. And if we take the trend here, it's a well-known picture. This works out like 50 euro cents per kilowatt hour. Say $1. So this means that a country has to generate 1 kilowatt hour to earn $1. And all those countries want to earn those dollars. The ability of China to build more power plants is the limiting factor for their economical growth. China builds a coal plant per week. Right. Well, this wouldn't be such a problem. You see these curves roll over at some point. This is the good news. This is, so they roll over where we stop making more material goods with our dollars and we start selling each other therapy. However, down there, there's 4 billion people living in that corner, and they want to move up. And even if they don't reach nearly our level of wealth, that already doubles or triples or even quadruples the energy use in the world. So there's a problem. We have to supply the energy. This is at the basis of basically everything that's wrong in this world. It is the divide between the poor and the rich. There's the pollution, it's the climate. It's in particular the geopolitical tensions, war and peace if you want. All the great political themes are captured by this picture. Well, there's more to say to that. The world population has been very low for a long time. Now there's a particular challenge for this generation because you have to solve this puzzle. We didn't solve it before, now we have to do it. Why is it that it's just us living in this very particular pivotal time? Well, this picture makes it clear. The world population has been very low for a long time and now it suddenly goes up. And where do we live? We live right there at the edge of this heaviside function. Life at the edge of the heaviside function. Well, this is what we do. If we were able to increase the population like that, by using more energy. And we were able to use more energy because we had a fossil fuel. Now let's have a look at the use of oil. There it goes. And on this scale, so there are hundreds of years here, there's just this little peak. And we have to realize that by the end of this century, we really should have finished using oil and coal and gas and things like that. The sooner we do that, the better. But it's just a blip here. So the challenge is that all this wealth that we have created and all these many people that we have created by using all that oil and coal, we now want to sustain and even grow while we are losing the source that we used to get here. Well, that's a big challenge. It's an enormous challenge. It's the defining issue of the century, as it's called. And again, it's up to us scientists to find a solution. Well, of course, there's more to that than those things I said. And as Steve has already pointed out to you in great, well, detail and eloquence, there's the climate problem. And I have just one picture. I'm giving the same messages with different pictures. Here we go. These are the fluctuations in the CO2 concentration. Here's the temperature fluctuations over hundreds of thousands of years. And maybe there's a correlation and maybe there's a causal relation. Maybe we don't know. So let's do the experiment. This is the experiment we are doing. And you're all invited to see the result. Okay, so these are the challenges. It may be clear that we have a very big problem. It was already clear, it is clear now. What do we do about it? I want the next. Oops. We do research. The next generations will have to find solutions or to implement solutions to the energy problem. To implement solutions, you need research first. There's about 50 years between the research and the implementation on the large scale of a new energy source. If we don't do the research now, our children and grandchildren won't even have the tools to implement solutions to the energy problem. So we have to do it. Now there's good news too. This is the oil price as it developed over the last decades. And this relates to the energy R&D budget. It's a very cynical picture, actually. It means that politicians, when the oil is expensive, think, we need research so that we have a solution 50 years from now. And the minute it's cheap, the budgets go down. But there's good news today because the oil price goes up. So follow the money. Our governments are realizing it. Europe is realizing it. Other countries are realizing it. We are going to do energy research. And there's going to be money for it. Good. So it's up to us scientists to give our contribution to saving the world. It's a big task. And we are going to have a lot of fun doing it. So from here I would like to start and switch to the fun part. And I was challenged to do experiments. And the experiment I would like to start with is a nice one. But you don't want to do it in front of 1,200 physicists. It's a particularly sensitive experiment and I need your full concentration. Now there should be a switch from computer to camera. It's coming, yes, very good. 1,200 Paulis and I do this experiment, it's unbelievable. Thank you very much. It was a bit nerve-wracking, but it's okay. This is really very sensitive. It's particularly temperature sensitive, and you're making a lot of kilowatts here. Anyone knows how this works, by any chance? Magic, you said? Magetic forces, yes. Yes, no, this was magnetic confinement. And while we're at it, why don't we build a fusion reactor? Now, before we build the fusion reactor, which is also based on magnetic confinement, I should like to sort of go through the basic principles with a simpler example. Does anyone have a lighter by any chance? Ah, very good, thank you. Yeah. Because if we want to build a fusion reactor, we want to burn the fuel, and you all know, of course, how this is going to work. It's going to be hydrogen isotopes and things. But if you want to realize what you need to actually get this thing to burn, maybe it's good to do this experiment. So we can do this with the lighter. Wow. Whose was that? You're a cigar smoker. It's your contribution to energy conservation. That's impressive. Anyway, this is a lighter, and suppose you wanted to design a lighter, maybe you want to first decide what you want to burn. It could be coal or peat, but gas is a better option. So you want to think about it. In this case, it's gas, and it makes a flame. Now, there's something about the choice of fuel, because after you have chosen the fuel, you have decided which chemical reaction you want to use, and this sets a minimum temperature. Here we go. You know what the temperature of this flame is? I do, now. Let's say 700 degrees or so. You can make a flame much hotter than that. You can't make it very cool, though. There's a minimum temperature. And this, of course, is related to this threshold energy in the reaction. It is very important to realize that. So what happens if we ignite the flame is we bring, for a short time, the temperature above this threshold energy. We get the flame, and now it has to sustain its own existence by producing heat. So there's also an issue of heat balance, power balance. You have to create a heat that keeps the flame above this temperature. And I can do an experiment to prove that by increasing the losses. So I make the flame, I blow, flame goes out. Right. This is all you need to know to build a fusion reactor. Let's now apply the same principles to fusion. So first we have to decide what fuel we are going to burn. And in this case, we just look in the textbooks and we find the easiest fusion reaction that wants to work. And it's the DT reaction, deuterium and tritium. And it produces helium and a neutron and a lot of energy. 17.5 MeV per reaction. It's a lot. If you want to know how much it is, I need a volunteer to come and help me with that experiment. Well, maybe Chris Buijink. Yeah. Yes, you. Welcome. Thank you for joining us. I should like you to take this glass. I hope you're a little bit thirsty. I opened a bottle so you know it's not been tempered. There's nothing but water in it. It's not enriched in any way, I'm afraid. This is ordinary water, but the fraction of this water is deuterium, fraction of it per mil. And supposing we were to fuse that fraction of deuterium with equal amounts of tritium, we could produce energy with this reaction. Now, maybe you want to take a sip. Don't drink it all at once. Sometimes you have to repeat the experiment, but maybe you want to take a little bit of the water and then feel that surge of energy flowing through your body. That was very little. Now, maybe you can estimate how long you could run your household on the amount of energy that you just swallowed.
I'm going to faint. No, I don't know.
You don't know?
No.
What guess?
You just say.
No, I know.
Yeah, you know.
Usually we get there. With the poll, it turns out that in a democratic approach you get the answer just right, but maybe you want to have a first guess.
Who knows?
Yeah. A week?
A week.
It's a week there. It was a very small sip, though. And it depends a bit on your house.
Yeah.
Week. Anyone more than a week? 2 weeks here? 1 year. That's very optimistic. Well, thank you very much. I think a week is just on the spot.
Okay.
A week for a glass of water, or sip of water, a month for a glass, a year for a bottle. And there's a lot of water in the South Sea sources. Thank you very much for joining me at this experiment. Ladies and gentlemen, there's a lot of energy in the water. There's plenty of fuel. If it's just a deuterium, there's for 50 billion of years. And usually there's a strategist in the audience who then says, that's nice, but what do we do afterwards? But the fact that there's plenty of fuel doesn't mean that it's easy. And the catch, of course, is that this fuel wants to burn only at a temperature of 100 or 200 million degrees Celsius. Sometimes people complain about Celsius, Kelvin. And of course you realize what happens if you heat any material to that sort of temperatures, it becomes a plasma. Now, many of you are solid state physicists. Maybe you don't meet plasmas that often. So we brought a few. Let's do a few experiments. I'll show you how easy it is to make a plasma and how easy you can manipulate them. So here's a tube. We are going to evacuate this. It's just air. It's not just air. It's mostly air that has been breathed by well-known physicists by this time. I'll switch off the pump so we evacuate this tube to some lower pressure. I apply a voltage between here and there. This is just 50 hertz transformed up to about a kilovolt. And here we go. I hope this is visible. We produce a plasma. Very easy. And of course, you know those are charged particles, and to prove you that these are charged particles, I borrowed a magnet from Jan Kees Baan's lab. And let us see what it does with the, maybe I can see this. Ah, yes. Yesterday I practiced all day and I managed to make this the FOM logo. But somehow it doesn't work with an audience. Thank you. So, let me switch this off. A TL tube, of course, is also filled with a plasma. The electrons, there are not so many of those, but the electrons reach a temperature of about 10,000 K. You can make this burn by just heating the gas. So here I have a microwave oven. Well, something like it. It's just a watt or 2 watts or so. This is a microwave emitter. I switch it on, apply the power to the tube. There we go. Oops, you see, no wires. Right, so it's easy to heat a plasma. Other devices you can buy in the shop. They're so-called conversation pieces. You put it on your desk in case the conversation doesn't flow. Plasmas are beautiful. We make them in the laboratory, but of course they don't exist on Earth very much. But the universe is filled with them. 99% or so, or much more than that, of the visible matter in the universe is in the plasma state. Right, so plasma, we know all about it now. Last thing, you need to worry about heat loss if you want to heat something to a few hundred million K. So we are going to isolate, to insulate, and we are going to do that as best as we can, and at some point you reach the theoretical limit. You can't insulate any better. What do you do then? If you want to prevent something from cooling down, you have done the best you can in insulation. Yeah, this is a difficult one. Insulation is easy to guess, but the other half is difficult. Well, you make it bigger. Big things cool down more slowly than small things. You knew that. The smallest animal that Mother Nature could produce, smallest warm-blooded animal to be precise, is the mouse. Any smaller can't produce the energy to heat itself. Likewise, the elephant is the biggest warm-blooded animal that can survive. If you make it any bigger, it melts inside. Right. So the strategy is clear now for the fusion reactor. We want to burn deuterium and tritium. We burn it at a temperature of a few hundred million K. It will be in the plasma state. We make a reactor. If it doesn't work, we make it bigger. Right. So here's our reactor. Let's first put the gas in an oven. Here's the deuterium and tritium. We apply the microwave heating. So this is very much like this tube, actually. We put that on. This becomes a hot gas, and then it becomes a plasma, so the electrons and the atoms go apart. We put more heating. Will this be heated to 100 million degrees? No, of course not, because it talks to the walls. Can never heat very much. So we think of this experiment. We get the magnetic field. Actually, applying a magnetic field here will reduce the cross-field heat diffusivity by 14 orders of magnitude. So applying the field is a good idea. At the same time, it means that you have to make this tube 10 to the 14th times as long as it's wide to get rid of the end losses. This won't work. We thought very long about this, and physicists are smart, so we invented the wheel. Thank you. So if we get rid of the end losses, it looks like this. If you give this sketch, which you and I have invented here in 7 minutes or so, if you give this sketch to an engineer, he'll build something that looks like this. Now this is ITER. ITER is the big fusion reactor that's presently under construction in Cadarache in the south of France. It's a world project. You see the toroidal chamber, there's a plasma inside, there are magnetic coils around it, and then there are all sorts of ports to look into it. ITER is a physics experiment, but it's also a political adventure. Because this is a joint project of 7 countries, or more than countries, in the world. So when the ITER treaty, ITER is an international organization, there are only very few of those, was signed on the 21st of November, a year and a bit ago, in the Élysée in France. So Mark Westerau is here, and myself, we're here, like here. And in the middle you see Chirac. There are 2 presidents, Barroso, Chirac, and then there's the Commissioner Potočnik, and then there's the ministers from the 7 ITER parties. So that's the United States, India, Japan, China, Korea, and the Russian Federation. This represents more than half of the world population. Well, if this is such a political adventure, it also means that presidents say important things about it. Sometimes it's nice, sometimes it takes time. When China, for instance, joined ITER, it said China wants to be among the first countries to employ commercial fusion power. Now, if there's one thing about which China doesn't make jokes, it is their energy policy. This is bloody serious, and the Chinese have a very fast-growing fusion program. They're very competitive. Likewise, the Koreans, who have said in a similar statement, we want to have commercial fusion power in 2040, and they're very serious about those research programs. Europe is leading in fusion, and Potočnik has said these things, so Europe wants to be leading and want to stay leading in this field. But also notice, he does that, he's convinced that we need to do that for a safer and sustainable future for our planet. He's also in the business of saving the world, so we're not alone. But it's very serious. Well, it's very political. At this moment we are building ITER, but we have other machines, and one of those is JET, the Joint European Torus. It's in England. It looks like this. It's been there since '84. It's at present the largest tokamak, as these machines are called, in the world. Holds all the records, or many of the records. And otherwise it's very similar to ITER. ITER is just twice as big as JET. If we go inside here, it looks like this. This is the toroidal vacuum chamber. The man gives an impression of the size. If we take the man out, or we leave him there, but we put the plasma in, it looks like this. And here we start the plasma. And this is what it looks like. Now you can see that we can confine this plasma, and here we can reach 100, 200, 300, 400 million K and confine it, and it's stable. It looks like this. No problem. It's a very boring movie. It just stays like this. So if you don't mind, we go on. Now it looks very stable and quiescent, but partly this is a trick. Partly this is because it doesn't make any light inside. But it sounds like this. If you put a magnetic coil to this plasma and you record the oscillations, this is what you hear. Okay, not a soft landing, this one. So there's a lot of magnetic activity going on. Now, you can simulate in the computer what goes on. I mean, maybe it's not entirely right, but it looks like this. So this is a simulation we did at FOM by a PhD student, Erik Min, who is now who received his PhD a year ago. You see these magnetic modes rotating and sending off turbulence in all directions. Now we did something to the plasma. We shot in a little ice pellet, real hydrogen ice. This made the plasma quiescent for a while, and then the turbulence comes back. You see this mode is always rotating there, producing all these turbulent eddies. The turbulent eddies we don't want, basically. They are bad for confinement. They get rid of energy at a fast rate. So we want to control those things in the center. And how do we do that? Well, of course, you can't stick anything into the plasma, so you have to do it by remote tools. And the remote tool is microwaves. So here's how we go about it. This is an experiment we did at an experiment in Germany. It's a FOM experiment. So there's microwaves. We send them in via a few steerable mirrors, and we focus that beam exactly in that turbulent eddy, in that island, a magnetic island as we call them. And this will stabilize that mode. It will get rid of the island. Sometimes you actually do want the island, so then you try to do the reverse process. And this works, but you have to know where the island is. So now, the latest, and this is real, this is something of a month ago, we use the same antenna to measure the signal from the island. Now this sounds obvious, but in goes a megawatt, and we measure a nanowatt through the same antenna, separating those two powers. And this works, 15 orders of magnitude difference in power levels, separated and measured. Well, this then goes into a feedback scheme, so we can do a feedback control on those turbulent eddies. And of course, we also need some input from other diagnostics. And very important, in that computer, we need an integrated model of the plasma. This is a very big issue at the moment, worldwide. We are part of that. And I like to say here that we also collaborate with Eindhoven University on this particular bit of the feedback of the turbulence in the plasma. Well, how does this look in ITER? Here's ITER again. So now we don't want to control turbulence. Our ambitions go further. We want to control the burn in ITER, because ITER will be a burning plasma. It will produce its own heat, its own turbulence. We still have to control it. Well, this is ITER. As I said, there are those holes, those diagnostic ports, and those red plugs, port plugs, are the things you can stick in and do something to either measure or manipulate the plasma. And we are involved as FOM in the manufacture of a few of those. This is a diagnostic tool. This is a spectrometer. We developed that together with partners in a new partnership in the Netherlands, set up especially to participate in ITER. So this is TNO, FOM, and the NRG in patent together forming ITER-NL. And the ITER-NL consortium was set up and signed in the presence of the Minister of Economic Affairs and the Director of Research of the Ministry of Research and Education only 2 months ago with a special budget, earmarked budget from the government. We make these things. Also, the microwave beam, the steerable microwave beam, it looks like this in ITER. It's a very big thing. All those things are developed in European consortia. It's not just FOM. We are integrated in Europe. And we work together with companies in the Netherlands and in Europe to make these things happen. They're very difficult to make. Right. Let me tell you a bit about fusion, the challenges in research of fusion. But I'll go very quick because there's little time. Well, you've seen we need to make a hot plasma. But you've also seen that we know how to do that. We have seen that we need to control that with magnetic fields, and you have also seen that we know how to do that in the tokamak. This works fine. Then we need to control the turbulence, and I've given you an impression of how that's done. Of course, this was only a very brief impression. But let's say that's under control. Now that hot plasma is in interaction with the wall at some point. You can imagine that this is a problem. There's a huge power flux, a huge particle flux, and those particles are hydrogen, so they're very corrosive. What happens there? Well, we have a research program on that, and also that we do in FOM. It looks like this. We have set up an experiment. We are building a very big one, and we have set up a pilot. And it looks like this. Here we go. So we make a plasma beam, and we put that on a target. And then we measure the erosion, and then we go about tricks how to prevent the erosion of the wall. You can imagine this is very important for ITER. In fact, it's a key issue for ITER. And we are setting up a laboratory. It's called Magnum PSI at Rijnhuizen, FOM Rijnhuizen. And this will be one of Europe's PSI laboratories where research for ITER is done. Okay, so now we have solved, or we are working on, 4 of the 7 issues. There are 3 more. 2 are very technological. They're not really FOM areas. One is the fuel cycle. It's not at all easy because every neutron that we produce in the fusion reaction has to produce a tritium, because the fuel we bring to the fusion reactor is actually lithium. The lithium is put in a blanket around that plasma, and we capture the neutrons from the fusion reaction in the lithium, makes a tritium. The tritium is fed back into the reaction. You have to realize every tritium has to cycle 1,000 times through the reactor before it actually reacts. It's not easy. We are not involved in that. Then all those neutrons will bombard the structural materials of the reactor. That is also very difficult. This is a real materials program. We need self-healing materials if you want. Higher temperatures, more mobility. This is a program that we might start, we might be involved in. This is certainly something that the fusion community in the world has to tackle, as we are not far enough there. This is a lot of research that needs to be done. And then finally, a fusion reactor is a very complex device. ITER is probably the most complex device ever built by mankind. The number of elements, of components in ITER is 10 million or so. This is comparable to an aircraft carrier. But here everything is integrated. So the complexity itself is one of the very big issues in fusion reactors. Well, so this was ITER and the 7 research challenges. How are we doing? Well, let's have a brief look back. Of course, one measure for success is power multiplication in a fusion reactor. And you want to have more than one. One doesn't make a reactor, 10 or 20 makes a reactor, it doesn't need to be infinity. The target for ITER is 10. We come from far, it was a long road, and here's our Moore's law, if you want. We compare it to the actual Moore's law for transistors. It turns out we are not doing so bad. In fact, we are a bit faster. Nobody complains that their computer power, well, maybe you complain that computer power is not growing fast enough, but still the sense is that if you buy a computer, you walk out of the shop, it's outdated. The same as fusion reactors. If you make this extrapolation, you get ITER there. Ah, that's 3 years ago. Now you realize when I showed the plot of the R&D budgets for energy research, not just fusion, I mean across the board. The 90s, late 80s and 90s were a very bad time. All sorts of research was stopped at that time. And certainly it was a very bad time to argue that we needed to invest $5 billion in something like ITER. So those plans have been sitting on the shelf for about 10 years. We could have had ITER 5 years ago, but we didn't take the decision. And this is real lost time. So now ITER moves there. We could have had it, and we still have to build for 10 years. Anyway, this is where we are. So the roadmap then looks like this. We have JET. You have seen JET. This is the present machine. We should have had ITER. We're building it now, so we get this in 10 years. This is tenfold power multiplication. It's still not a fusion reactor. Then we want to make a demonstration reactor. We could have that pretty soon after ITER. Let us say 10 years after ITER. Still not saving the world. Then we need to make commercial plans. Probably the expectation is that all those countries participating in ITER will each build a demonstration plant, and then there'll be maybe a first generation of 10 or 20 commercial plants. Still not enough. If we want to make an impact, we need 1,000 reactors. And this is something we have to realize, that whatever you do with the energy problem, we have to build the equivalent of a 1 gigawatt power plant, but in a sustainable way, with sustainable technology, every day from now on, and we have to increase that rate to 3 per day by the end of the century. And this is an immense task. It's almost inconceivable, but we have to do it. Well, while we're thinking about that, maybe the question comes, will fusion come in time then? Because we have all the time to come. Well, this is a very important plot for me. So here's global CO2 emission. Let's take the CO2 emissions as the driver of our timescales. There are other drivers too. Here are the global CO2 emissions. Of course, they have been rising very quickly. And if we keep using oil and coal, they'll keep going up. We can't accept that, so we have to bring this down. The number 550 parts per million is the level where the CO2 concentration in the atmosphere would concentrate if we stayed on that line. Basically, all the CO2 that is emitted stays in the atmosphere and is only very slowly absorbed by the Earth. Well, you see that the 550 parts per million, you know we come from 280, we've been there for very long, now we are at 370 or so. 550 is considered as the most ambitious goal that is actually realistic. But it still goes up for a long time. Well, those are the one power plant per week that those developing countries, economically developing countries, are building. We are not going to stop that very quickly. And every power plant we build today will be there for 50 years, you have to realize. What we decide today will define the energy infrastructure for the coming 50 years. But then we have to bend it back. But in this plot, you'll find that only after about 50 or 70 years, we are back at the level we are now. And only then does the emission really go down. Well, if we go further, yes, you'll find that the big challenge, I mean, now we're talking with Kyoto about this red line, really about this, it's too short, I'm afraid. But you realize that what Kyoto does is keep us on the red line between 2000 and 2010. Well, that doesn't look like a big challenge on this graph. Still, it's creating a lot of waves. The real big challenge is 50 years from now. Then this gap opens. When the demand is growing, and we have to bend down this red curve. And we need new energy technologies to fill that gap, and many of those are in the research phase and will only be available then. And fusion is one of them, and I think that we'll need every technology that we can think of, and certainly in the research phase we'll have to develop everything we can put our hands on. And if someone solves the problem, we're all happy. Well, let's see how our counters are doing. We lost 25 minutes in solving the problem. Counters have been going on all the time. Let us enjoy this evening and tomorrow start solving the energy problem. Thank you for your attention.